Welcome again in the course module of Communication Engineering. So in the last lecture, we have started digital modulation scheme in which we have already seen the amplitude shift keying and phase shift keying. So now today we have to further discuss few more topics. Okay, so let's see. Today I'm going to discuss two more such digital modulation schemes, namely quadrature phase shift keying, which is also called as Quadri phase shift keying technique, and another one is our frequency shift keying technique. So I will first start with the Qpsk technique, which is quadriphase shift keying technique. So that we have to look at first. Okay, then we will be discussing about the FS keying. So as I said, in the case of phase shift keying technique, which is also known as binary phase shift keying. So I told you that in this case, what we have is we have to take a binary data sequence, and then basically this binary data sequence has to be converted into the polar non-return to zero signals. Okay, and then this has to be multiplied with the appropriate basis function, and then based on the polar non-return to zero signal, whether it is +1 or -1, okay, this signal has to be multiplied, and therefore the signal that will be sent over the band pass channel will be having either 0-degree phase shift, or maybe it may be a 180-degree phase shift. Okay, so that we have already seen in the previous lecture. Now today we have to look at the Quadri phase shift keying technique. Okay, so let's start this discussion. Okay, how this Quadri phase shift keying technique will work. Okay, that we have to look at today. Okay, so let's see this Quadri phase shift keying. Okay, Qpsk. It is also called as Quadrature phase shift keying. Okay, so first you try to understand its mathematics. Then I will be telling you what will be its signal space diagram, what will be its like output. Okay, so that we have to look at. So first you try to see that basically in the case of binary phase shift keying, for a single bit, like either it may be a 0 or it may be a 1. Okay, there was a corresponding phase shift in the carrier we have observed. Okay, so that was like for 1 it may be like there is no phase shift, and if it is 0 there may be a 180-degree phase shift. Okay, so that we have already seen in our previous discussion of the BPSK. Now today we have to look at, suppose that we do not want to have a phase shift due to just a single bit, but rather what we want is we want to take the combination of 2 bit to make a phase change in the carrier. Okay, so what I'm trying to say is that in the last case, for a single bit change, okay, whether it is a 0 or 1, okay, there was a corresponding phase change in the carrier that we have already seen. But in the case of quadrature phase shift keying, the combination of 2 bit, like it may be 0 0 0 1 1 0 or 1 1, is going to decide the corresponding phase of the carrier. Okay, so last time when we discussed about the BPSK, we have seen that only 2 possible phases are there. Okay, so one was 0-degree, or maybe it may be a 180-degree phase shift. But in the case of quadriphase shift keying, you will find that there are total 4 possible phase shifts. Okay, that can we have. Okay, so basically you try to say this mathematical expression first. Okay, so let us say that in the case of quadriphase shift keying technique QPSK, the signal that will be defined is by actually this particular expression. Okay, so it is having this factor root over 2 EB by TB, and then we have the cosine function 2 pi FCT plus 2I minus 1 pi by 4. Okay, so this will be the signal that will be present during the this particular time interval 0 to TB, where TB is our bit duration. Fine. So now what we can have is we have, let's try to first try to understand this expression. Okay, So what this expression tells us, okay, that we have to first try to understand, because this expression is having a certain means during the this bit interval TV, okay, 0 to TV, there will be a certain energy of this particular carrier that going to be have, okay, that will be our EB. Okay, we have already seen that this can be further written as root EB, root 2 upon TB cos then this function. Okay, so this is our bit energy, you can say that. Okay, it is a bit energy. During this bit, whatever the carrier we are sending, it is the energy of that particular carrier. Now we can see this expression represents that we are having a cosine function, and this particular carrier is having its frequency equals to FC. Now, generally, as I said, that in the case of binary phase shifting, we are having just two different phase shift in the carrier, that 0 degree and it may be a 180 degree. But in the case of quadrature phase shifting, we are going to have total 4 phase shift or four different phases of the carrier corresponding to different combination of the bits. So here the I will take 4 different values, and this I can be like it is from 1 to 4. Okay, so this I can be 1, it can be 2, it can be 3, it can be 4. So based on these values of I, we can calculate what will be the carrier phase. Okay, because this is representing the phase part. Okay, here you can see that this is representing the phase part. So here we can see that if I substitute, let us say I equals to 1, then you are going to get this value equals to pi by 4. Okay, so this phase will be equals to pi by 4. Similarly, if you substitute I equals to 2, you are going to get this value equals to 3 pi by 4. Okay, when I equals to 3, we will be getting 5 pi by 4, and when it is I equals to 4, we are going to get it as 7 pi by 4. So basically, we can see that there are total 4 phases of this carrier. Okay, so corresponding to different values of I. Fine. So those phases are nothing but our pi by 4 and 3 pi by 4, 5 pi by 4, and 7 pi by 4. So now let's discuss it further. If we expand this particular expression a little bit, okay. So just you try to expand this expression by following the formula of cos A plus B. Okay, so I hope you must be able to write this particular expression. Okay, it is cos A cos B and minus sin A sin B. Okay, so this way we can write this particular expression. Okay, so now again we already seen that this I is actually taking this 4 values 1, 2, 3, 4. Okay, and based on this values of I, we are going to have a different phases of the carrier. Now from this expansion, what I can have is I can write this expression, okay, in this form. Okay, let us say the signal SIT will be represented by a certain signal SI1, okay, multiplied with the a basis function phi 1t minus SI2, because here we have the minus sign. I am just substituting minus sign here. Okay, and then we are having another signal SI2, okay, t, and another basis function phi 2t. Okay, so basically see what is SI1t that we have defined in this particular expression. So our SI1t will be root over EB. Okay, root over EB, and then this function cos 2i minus 1 pi by 4. Okay, so this is, we have called it as like our SI1t. Okay, so this is our SI1t. Similarly, you can write this SI2t equals to root over EB, and it will be sine 2i minus 1 pi by 4. Okay, so if you keep this term separately, if we are writing this term separately, then you must be able to answer that what will be the basis function. So obviously our basis functions are root 2 upon TB, then cos 2 pi FCT, and here it is root 2 upon TB sine 2 pi FCT. So these are the two basis function. Okay, so these are the two basis functions. So we have this basis function, and these are the two signal points, you can say. Okay, so now from this basis functions, and these are the two signal points from this particular expression of SIT. Okay, we can have the different message points. Okay, we can find out the different message points by having this particular expression. right? So that we have to understand, okay? By having this, we have to also derive what will be the waveform of our quadriphase shifting signal, okay? What will be our waveform of Qpsk signal? So let's try to understand this. So because this is two orthonormal basis function, we got phi 1t root over 2 upon tb cos 2 pi fct and phi 2t root over 2 upon tb sin 2 pi fct. Okay, so we have got these two orthonormal functions. Okay, now you try to see this waveform. Okay, I just request all the viewers, please, you can prove that this particular function is orthogonal. Okay, because I am writing here it is orthonormal basis function, so it means that these two functions are normalized functions. Okay, phi 2 and phi 1t in itself, they are normalized functions. So normalization I have already proved in my previous discussion. And again, these two functions are orthogonal. Okay, so this must be orthogonal. Okay, so you can prove it. Okay, you can prove it. It must be an orthogonal function. So you can just calculate the integration over 0 to tb, and then you can multiply this two function, and then you can integrate it. Okay, that integration should come out as equals to 0. That will be showing that these two functions are actually orthogonal to each other. Now you try to see in the case of quadrature phase shifting, what happens is, let us suppose that this is our input binary sequence. Okay, let us say this is our data. Fine. So once we have this particular data, then what we can do is, first we need to divide this all the binary sequence into die bit. Okay, so what is this die bit means? It is the combination of the two consecutive bits. Okay, so let us say this is our sequence 0 1 1 0 1 0 and 0 0. So I will take the first 2-bit, okay, combination, that I will be calling it as a die bit. Okay, so I will be calling this die bit as 0 1. Then it is a die bit, another die bit we have is 1 0, and then another die bit is 1 0, and then the last die bit is equals to 0 0. Now, based on this, what we can get is, first we have to get this particular signal. Okay, Si1t, phi 1t. Okay, this is our first signal. So this signal first we have to, this waveform we have to first plot. So here you can see that in this case, if you see this Si1t is actually multiplied with the basis function phi 1t, which is a cosine function. Okay, it is a cosine function. So now here what we can do is, first we will be taking the odd numbered sequences. Okay, all the odd numbered sequences means that if we are having this die bit, okay, we are having this die bit, you can see that this is the first bit. I can call it as a first bit, this is second bit, this is third bit, this is fourth bit, fifth bit, sixth bit, seventh and eighth bit. Okay, it means that this all odd number bits. So here the odd number bit is our 0 is the odd number bit because it is first bit. Okay, similarly third bit will be our odd number bit, the fifth bit again is our odd number bit. Okay, so what I'm trying to do is, first I'm dividing this, I'm just writing all the odd numbered bit. Okay, so all numbered sequence we have to write. So this odd numbers are our 0 bit here. Okay, 0th bit, and this is 0 bit, this should be 0, and this is the third bit is our equals to 1, our fifth bit is equals to 1, and our seventh bit is equals to 0. So this is our bits. Fine, this is our odd numbered bits. Now the polarity of coefficient Si1. Okay, so that we have to look at what will be the polarity of this particular coefficient Si1, that we have to try to understand. So whenever we are going to get 0, okay, so first what we have to make is that whenever we are going to get this value equals to 0, that time whatever be the phase that should be negative, that we have to take into consideration. Okay, whatever be the phase that should be the polarity of this coefficient should be negative. Okay, this is our convention that we need to follow. So whenever the our odd numbered sequence bit is equals to 0, this polarity of the coefficient Si1 that should be equals to 0. Similarly, whenever it is 1, it should be taken as positive. Okay, you try to first understand this is convention. Okay, so we have this odd numbered sequence 0 1 1 0 we have taken, And then corresponding to 0, this polarity of the coefficient of this SI1T that we have to take is equals to negative whenever we have the 0. Okay. Whenever it is 1, we have to take it as a positive. Again, whenever we have 1, it is positive. Whenever we have 0, it is negative. So if you calculate the SI1 multiplied with the phi 1t, okay, so phi 1t is nothing but our cosine function. Okay, so when we have the cosine function and when we have occurred this bit equals to 0, at that time what happens is this polarity is going to be negative. Okay, as per our convention, whenever this odd number sequence is 0, this polarity should be negative. So we know that for the cosine function will start from the top. Okay, and then it is going like this, and then it will be repeating in this fashion. Fine. So it should start from the top. Okay, but because we have to multiply with the negative, so that value was means cos 0 should be equals to 1. But because of the polarity is equals to negative, this will become -1, and therefore you can see that this waveform has been started from this particular point. Okay, so now this waveform is actually repeating in this fashion. Okay, it is coming in this fashion. Now this waveform will be keep repeating for the entire duration of 2 TB. You remember that the bit duration is equals to TB, and that bit duration is corresponding to only one bit duration. Okay, it is 0. But this waveform has to be repeated for the duration of 2 TB. You remember that. Okay, so this waveform is actually repeating for the duration of 2 TB. Now, when this odd number sequence is equals to 1, okay, here you can see that this particular bit is equals to 1, then the polarity should be positive. Okay, so positive means we have this cosine function. So this again has to be started with the cosine function itself. Okay, so this is coming here, and then it will be repeating for the duration of 2 TB. Again, we are going to get this positive, so the polarity should be kept positive. So again, the same waveform will be keep repeated. Okay, till next 2 TB duration. Okay, so again here we have got this negative sign because of the odd number sequence equals to 0. So this negative will make a 180-degree phase shift, and we are going to get this particular signal. Fine. So this way we have got this odd numbered sequence signal SI1T of phi 1T. Okay. So this way we have got this particular waveform. You might be wondering how we have got and why we have just taken the this one bit only. Okay, why we have just taken this one bit? You must be wondering at this particular point. But when I discussed about the transmitter part of this Qpsk system, that time you will be more clear about why we are actually first considering only one bit. Okay, we have not taken the second bit. Okay, and then first we have generated this type of waveform, and then again what we have to take is we have to take the even numbered sequence. Okay, so this is our first bit, so our second bit will be this one. Okay, so this is second bit, this is fourth bit, this is sixth bit, and this is eighth bit. Fine. So now we have to take all this even numbered sequence. Okay, this is 1, this is 0, then again 0, and then again 0. So again, a similar convention we have to follow. The polarity of the coefficient SI2, if you see, it should be positive. Okay, so it has to be positive. So if you take this as a positive, fine. So we have to just plot this SI2 phi 2t. Okay, this multiplication we have to plot. So we can see that this phi 2t basis function is nothing but our sinusoidal carrier. So because this polarity should be positive, here you can see that this polarity SI2 t should be positive, that we have to taken as per our convention. Okay, whenever it is +1, okay, if it is 1, then it should be taken as positive. If it is 0, then it should be taken as negative. So here again we are going to get the sinusoidal wave. Okay, and at this time again it is repeated for a duration of 2b time. Okay, 2 TB duration, and then again here you can see that because of the occurrence of the 0, the polarity should be negative. So there will be 180-degree phase shift in the carrier. You can observe here, and then this carrier will be keep on repeating because all the other bits are equals to 0, 0. The same carrier will be keep on repeating for the next 2b. 2 TB duration. Okay, so up to this particular bit 0. So this type of waveform will be generated. Okay, this type of waveform will be generated. So whenever there is a bit change or polarity change, you can say there will be a phase shift of 180 you are going to observe in the waveform. Fine. So you can understand that this two waveform is corresponding to our binary phase shifting waveforms. Okay, it is similar to our BPSK signal. Okay, because we know that in the case of BPSK signal, whenever there is a 0, there was a 180 phase shift, there was a 1, and there were no phase shift in the carrier should take place. A similar waveform we have plotted in this particular case. Okay, a similar waveform. The only difference is that here we have taken the first bits, all the first bits have been considered. Okay, and so all the odd bits have been considered first, and then here we have considered all the even bits. Okay, and then our basis function here is cosine and here is sine, and correspondingly we have plotted this particular waveform. So now once we have this two waveform, okay, once we have these two waveforms, then this final waveform can be generated by following this particular expression of SI1t phi1t minus SI2t phi2t. So by having this particular expression of SIT, we can generate this particular waveform. You remember that, okay? We can generate this waveform, and this waveform is corresponding to our like Qpsk signal. Okay, so this particular D is actually representing the Qpsk signal, which is the subtraction of this and this particular signal from this signal. Okay, and then we will be able to get this particular result. So I hope you must be able to understand this particular picture, how this picture we have got. Okay, so this way we can get this particular result. Now, once you have able to follow this one, okay, if this waveform, if you are able to follow, now let's try to see this the signal space diagram of the Qpsk signal. Okay, that we have to first look at. So you try to see whenever we have this Qpsk signal, as I said that the input should be a die bit. Okay, it should be a combination of two binary bits, and based on this combination, we are supposed to get a corresponding change in the phase of the carrier. Okay. So for example, if suppose that if we substitute certain values, okay, then we can calculate what will be the value of SI1 and SI2. Okay, these are the two coordinates of message points that we have, SI1 and SI2. Okay, so that we already have. So if you see this particular expression, okay, you can see this particular expression. So here, for example, it is a gray encoded input die bit that we are saying. Okay, so when this gray encoded input die bit is 1 0, then the corresponding phase of the Qpsk signal is pi by 4. Okay, it is pi by 4. When it is 0 0, it should be 3 pi by 4. Okay, so how it is coming like this? Okay, that we can directly see from this particular expression. Okay, we have this particular expression. So even you can substitute here, you can find out. Okay, so let us say that when I equals to 1, if you substitute in this particular expression I equals to 1, what will be the result that we can got? So here you can just try to calculate in this particular expression. When we substitute I equals to 1, here the value that we are going to get is cos pi by 4. Okay, so cos 45 degree is equals to 1 upon root 2. Fine. So this value will be 1 upon root 2. So what will be this coefficient SI1t when I equals to 1? It will be root over EB by 2. Fine. It will be root over EB by 2. Similarly, when you substitute here I equals to 1, this coefficient is again come out as root EB by 2. Okay, it will be coming out as root EB by 2. So that we can see directly from this expression. Okay, so this two both the bits, okay, the output of this particular two signals that we are going to get, or both the coefficients are going to be positive. You remember that it is root EB by 2, root EB by 2. So this both the coefficients are going to be positive when we substitute I equals to 1. Similarly, when you substitute I equals to 2, you can find it out what will be the value, because it is 3 pi by 4. Okay. So when it is a cosine function, and when we talk about 3 pi by 4, okay. So I hope that this 3 pi by 4 should be a negative value. Okay. So you can calculate that it is a negative value. Similarly, you can again calculate when I equals to 2. This value is again 3 pi by 4. So for the sinusoidal wave, what will be 3 pi by 4? So pi by 4 is 45 degrees. So 3 pi by 4 is 135 degree. Okay. So here you can see that this is a sinusoidal wave. So at this sinusoidal wave here you can, this is 90 degrees. So here somewhere here you are going to get 135 degree. Okay. So at this point we are going to get this coefficient that will be again like root over EB by 2. Okay. That will be a positive value. Okay. But in the case of cosine, okay, if it is 135 degree, then here you can see that it has been started from this, and then you can see that this is the cosine wave. You just try to see this, this is a cosine wave. So this is our 90 degree, okay. So when it is 90 degree, here it is somewhere it is 135 degree, fine. So when it is 135 degree, then this value is coming out as negative. So it means that when I equals to 2, this particular coefficient, okay, this particular coefficient SI1T is going to be negative, and this is going to be positive. So initially for I equals to 1, both the coefficients were positive, okay, positive, positive, and that value was equals to root over EB by 2, okay, and plus root over EB by 2, for both the coefficients. But when I equals to 2, this value is coming out as negative, and this value is coming out as positive. Okay, so similarly, you can just try to observe here. Okay, just try to make this observation. Okay, so when we have this results, okay, coordinate of message points, fine. So when we substitute I equals to 1 or 2 or 3 or 4, okay, whatever the values if we substitute, okay, so that value you can see that if you also consider this negative sign, okay, you try to see this one, okay. So if you consider this negative sign also, for example, okay, because here we have the negative sign also. So if you consider this negative sign, so including this negative sign, if you see the coefficient of this particular basis function, so whenever it is coming out as positive, it will become negative. Whenever it is coming as negative, it will become positive. Okay, so here you can see that initially when it was coming as negative, okay, at that time it should be coming as means it was coming as positive, then it should be coming out as negative. Okay, you remember that. So this was our negative value, fine. So that you can try to just substitute, okay, the different values. You try to first you substitute the different values of I, and then you try to get the different coefficient value of SI1 and SI2, as I said in the previous discussion. Okay, so you try to calculate those points, fine. So once you will be able to calculate those points, what you will find that there will be a corresponding phase shift of pi by 4, and the corresponding coordinates of the message points that we are going to get is SI1 and SI2, that will be positive and negative. So if for this SI1 is positive and SI2 is negative, then whenever there is a positive, I will be keeping this corresponding binary bit is equals to 1. You remember that whenever there is a positive sign here, this positive sign means the corresponding binary bit should be equals to 1. So here I have just make it 1. Okay. Whenever it is negative, we just make the corresponding binary bit equals to 0. Okay, so now you try to just observe this all the signs and the corresponding gray encoded input die bit. Okay, so it is just like giving a certain conventions. Okay, you try to understand this. So whenever there is a positive, it should be 1. Whenever it is negative, there should be a 0. Okay, so here you can see that because sometimes the students may get confused why just is for 1 0 this is the code, why it is for 0 0 it is the code. So it is just for the sake of convention. Okay, whenever it is a negative, this corresponding to two die bits, that should be equals to 0 0, because this sign is coming out as equals to negative. Similarly, when this is negative positive, it means that it represents 0 1. Okay, when it is positive, it represents 1 1. Okay, so this way we are going to get a gray encoded input die bit. So why it is gray encoded? If you understood the gray codings, okay, you must be able to understand the gray code first. So if you have studied the digital electronics, then you must be able to know that what is the gray codes. So in the generally in the gray codes, this binary bit is just going to have only one bit change. So here you can see that it is 1 0 and only one bit change has occurred to the next number because only one bit is actually changing here. Similarly, from this 0 0 to 0 1, if we move, only one bit change has been occurred. Okay, only one bit is changed. Okay, similarly in 0 1 to 1 1, only one bit change is occurred because this 0 has become 1. But in simple binary code, if you see what is the sequence, we got 0 0 0 1 then 1 0. So from 0 0 to 0 1, when we move, generally there is a one bit change. But when we move from 0 1 to 1 0, okay, when we move from 0 1 to 1 0, there is a 2 bit change, because from 0 1 to 1 0, this 0 is becoming 1, and means this 1 is becoming 0 and this 0 is becoming 1. So there is 2 bit changes. Okay, so that is not a gray coding. Okay, so here it is, these codes are actually a gray codes. Fine. So you now first try to understand this signal space diagram. Okay, this is also a very important diagram. So you try to understand this important diagram. So you see that basically we have two basis functions. Okay, phi 1t and phi 2t. So when we have this phi 1t and phi 2t, so let us suppose that if on the x-axis, if I represent this phi 1t, okay, let us say this is our phi 1t, okay, because these two functions are orthogonal to each other, and then it is because having the same frequency. Here you can see that it is having the same frequency, but these two functions are these two basis functions are orthogonal to each other. So if I am representing this x-axis by the phi 1t, okay, then if you subtract 90 degree or if you add a 90 degree, okay, so let us say if you if you adding a 90 degree, okay, to this particular function, so cos something theta plus 90 degree, okay, so it is going to give you sine theta, but that value is equals to minus sine theta. You remember that. Okay, so if we have this as a cosine function, okay, if this is a cos theta, if this axis represents the cos theta, if you add a certain angle, okay, to it, if theta plus something, okay, at that time, if you're adding a 90 degree, okay, that time this particular function will become minus sine theta. You remember that. Okay, this function will become minus sine theta. When you're subtracting minus 90 degree, that time this will become positive sine theta. Okay, so that's why here you can see that in this particular axis, okay, here we are having the positive axis. Okay, for our phi 1t, here we have the positive axis. A positive magnitude is represented here, and here we have the negative magnitude of this particular basis function phi 1t. Okay, but on the y-axis, if you see, because this represents the phi 2t, okay, this upward direction, okay, this direction is actually representing the negative magnitude, and this downward direction actually represents the positive magnitude. Why? Because how to obtain the second basis function? To obtain the second basis function to this particular cos theta, okay, we need to add a positive 90 degree. If you add a positive 90 degree, you are going to get the minus sine theta. You remember that the value will be minus sine theta, and therefore this axis represents the negative value. If you want to subtract the minus 90 theta, okay, theta minus 90, then you are going to get this particular sine theta axis. Okay, so this axis will be your positive sine theta axis. So this way we are going to get these two axes, okay, that you have to remember. So now here again, what we can have is, so if we substitute a certain values, okay, for example, if you want to represent this particular gray code 1 0, okay, so this 1 0 represents this positive value and this negative value. Okay, so this is the magnitude. SI1 is the magnitude of our basis function phi 1t, and this SI2 is the magnitude of our basis function phi 2. Okay, phi 2t. So this is the magnitudes. Okay. So when our this if we want to represent 1 0, okay, onto this particular signal space diagram, then this 1 0 can be represented by this plus root e by 2, a coordinate point that represents these 2 points. Okay, plus root e by 2, and here it is minus root e by 2. So here it is in the books, it is written as e. So please make it EB, okay, because I have just directly taken the picture there. They have used the notation as equals to E, but in our cases we have represented the same thing by root EB by 2. So it is EB, okay, so just to make it EB. So basically if we want to show this plus and minus, okay, magnitudes, so on phi 1t, this particular point represents the magnitude equals to plus root EB by 2. And here this is actually representing on phi 2 axis, this is representing the magnitude equals to minus root EB by 2. So this is the point, okay, this is the actual point that represents our message point 1, okay. So this is our message points, okay, the coordinates of our message points, and that will be corresponding to 1 0. This is corresponding to the die bit equals to 1 0. Similarly, if you see this, because this axis is negative, this axis is negative, then the corresponding this particular bit, okay, that will be representing your message point 2, that will be representing your die bit equals to 0 0. Similarly, we can have our M3, which is 0 1, okay. So this is our negative value first, okay, and then we are having a positive value, okay. Then again we are having a message point for M4, okay, which is equals to 1. So I hope you must be able to understand this signal space diagram. So the only point that you have to understand that why this axis is negative, okay, why this axis is negative, okay, because here we have taken this positive, and then here we are taking the negative axis rather than taking this as the negative axis, as in the case of simple coordinate system. But here it is not the case, okay. Remember that phi 1t that we have taken is a cosine signal, and phi 2t that we have taken is the sine, okay, sine, okay, sine function. So because by adding the plus 90 degree, it will become minus sine theta, and therefore this axis will become minus, okay, this axis will become negative. Because in the anti-clockwise direction, the angle is measured in the positive direction, okay, this is the positive. If you are adding anything plus 90 degree, then this should be going, or this particular vector should be rotated in the anti-clockwise direction. If you want to subtract minus 90 degree, then in this way, okay, it has to be rotated in the clockwise direction. So that idea must be there to understand this particular signal space diagram. So I hope you must be able to follow this signal space diagram corresponding to different gray coded input die bits, what will be the corresponding message points. So now once you understood this one, okay, you can see that there will be a decision boundaries, okay, and obviously in this case the decision boundaries will be this axis itself, okay, this basis functions axis that we have chosen, this axis itself will become a decision boundary. Why? Because you can see that this represents our message points, okay, this represents our message points, these are the message points. So you can see that when we send the signal, then there may be a chances, because this coordinates that we have got due to the summation of both the basis function phi 1t and phi 2t with their corresponding coefficients si1 and si2, okay. So once we send the signal through the channel, because of the presence of the noise, this point may be either go in the upward direction, okay, it may be go to the horizontal direction towards this side. So it may fluctuate around this point, okay. So this fluctuation may be like this, this fluctuation may be like this fluctuation may be like this, okay. So this fluctuation may be like this. So basically this particular quadrant, this first quadrant, if we say this complete first quadrant is the region 1, in which if the signal lies if anything greater than this particular value, okay. So here we have the axis phi 2t, so anything any value which will come within this first quadrant can be considered as the message point equals to 1, okay. Any value, any magnitude that will come, that we will be detect, okay, if it is coming within this particular first quadrant, that will be considered as the message point equals to 1. Similarly, for message point 2, this entire second quadrant will be our region 2. Okay, you remember that this is our decision boundary. Okay, these two blue lines that we have drawn, which is nothing but our basis functions that also represent the axis of this particular system. Okay, axis of this particular signal space diagram is itself our decision boundaries. Okay, because it is the bisecting these 2 points. Okay, it is bisecting, it is the midpoint of these two message points. Okay, everywhere. Okay, again for these 2 points, this is also again a midpoint. Okay, this is also bisecting this particular 2 message points. Again, it is 2 message points, so it is bisecting it. Again, here it is having 2 message points, it is again bisecting it. So because this represents the middle points. Okay, and therefore this quadrant becomes the one reason. Another reason is this one: any message points that will come, any magnitude that will come within this quadrant, second quadrant, that will be regarded as message point 2. Similarly, anything that will be coming under this one will be regarded as M3, and anything that will come within this particular region will be called as M4. So that way we have this our Qpsk system and its corresponding signal space diagram. Okay, so now you try to see one more basic difference in the case of BPSK and Qpsk. So let us suppose that we have this particular binary sequence 0110 in the case of BPSK. Okay, binary phase shift keying. So as we know that in the case of binary phase shift keying system, whenever we have a bit equals to 0, there will be a corresponding 180-degree phase shift in the carrier that we are going to get. Okay, so whenever there is a 0, there will be 180-degree phase shift. There is a binary 1, there will be a 0-degree phase shift. Okay, so corresponding to this binary sequence 0110, okay, we are going to get this corresponding phase shift will be 180 degrees, 0 degrees, 0 degree, and 180 degree. So the meaning is that there are total, if you see, we are having total 4 bits. The corresponding phase shift in the signal or the carrier that we are sending is also 4 phase shifts that we are going to observe. So whenever there are total 100 bits per second, let us say that the 100 bits per second we are actually applying to this BPSK system. So that time what happens is a corresponding 100 phase shifts per second we must be able to observe at the output. Okay, you remember that because we are not sending the bits. Okay, in the case of digital modulation scheme, we are rather sending the sinusoidal carrier, high frequency sinusoidal carrier, okay, for a particular bit duration. And based on the like binary value 0 or 1, the phase of this particular carrier is going to change based on the modulation scheme. Okay, as in this case, it is a BPSK signal. Whenever there is a 1, there will be a 180-degree phase shift. That means 0. Whenever it is 1, it is 0-degree phase shift. So what we can actually observe here is this: if there is 100 bits per second that we are applying to this particular BPSK system, then the corresponding phase shift will be 100 phase shift we can observe per second. Now we try to again see the same thing. If we apply the same sequence 0110 to a Qpsk system, okay, then what will happen is because of 0110, first of all, this 2-bit will be considered. Okay, first, as I said that there will be no phase change corresponding to single bit, but rather we have to consider the combination of the 2 bit. So first we have to divide it into the combination of the 2 bits. So it should be a 0-1 and then followed by 1-0. So for corresponding to 0-1, here we can see that this phase change should be 5 pi by 4. That 5 pi by 4, if you see that may be coming out 225 degree. Okay, so it is coming out as 225 degree, or you can write in pi, means in the radians as 5 pi by 4. So that will be the phase change in the carrier that we can observe corresponding to 0-1. Similarly, corresponding to 1-0 die bit, okay, this value should be pi by 4. So you can write this as equals to 45 degree. So these are the 2 phase changes that we are going to observe in the case of Qpsk system as compared to your BPSK system. The meaning is that though the input sequence, if it is means having its number of bits per second that is coming to this particular system is 100 bits per second. But the output is actually having only 50 phase shifts per second. Okay, just half. Okay, because we are just changing the phase of our carrier based on the combination of the two bits. Okay, so if we are just sending the 100 bits per second, okay, but the corresponding phase shift in the sent signal, okay, will be only 50 phase shift per second we are going to observe. Okay, 50 phase shift per second. Okay, so basically we have one parameter which is called as the baud rate. Okay, you must be aware that what is bit rate. So when we are having a PCN system and then we do the encoding, the encoded bit will be directly transmitted through the our baseband channel. Okay, and that time this bits will be converted into a certain line codes, and then this codes will be fetched to our transmission line. So basically how many bits we are sending per second? Okay, we are sending like 1000 bits per second. Then I can say that it is 1000 bits per second we are launching to the transmission line, and then that signal is being transmitted. But in the case of digital modulation scheme, what we can see is due to the 100 bits per second that we are launching to the Qpsk system, the corresponding there are only two means carriers that we are going to send. Okay, because we are sending the carriers. Okay, high frequency carriers. So there will be only a corresponding change in the carrier phase that we can observe. So how many such changes we are going to observe, that will be actually means considered as the baud rate. Okay, baud rate. So please try to understand what is the baud rate, which is also called as the symbol rate. Okay, so how many such symbols actually we are sending? So when we are not means sending the carrier, but rather just we are sending the bits. So whatever be the bits, the same will be the baud rate. But here it is not the same, because these bits are actually manipulating the phase part of the carriers. Okay, and the two bits are actually changing the phase part, and therefore here we can just see that 100 bits per second we are applying, but there is a corresponding phase shift is equals to 50 phase shift that we can observe per second. And therefore what we can see that in the case of Qpsk system, this baud rate or the symbol rate, okay, you can see that this baud rate is equals to half of the bit rate. Okay, half of the bit rate. Similarly, if you can have like if we have the combination of 4 bits, okay, if it is a combination of 4 bits, so it is a combination of 3 bits, let us say, okay, then correspondingly you have to tell how many such phase shifts that we are going to observe. Okay, how many such phase shifts are going to observe, and that will be giving us the idea of baud rate. Okay, idea of baud rate. So now if you have understood this one, let's try to understand this Qpsk system, okay, in which we have the Qpsk transmitter and Qpsk receiver. So let's see this basically how it is done. Okay, first you try to see this. We will be having a binary data sequence. Okay, and this binary data sequence has to be converted into the polar non-return to zero signaling. Okay, polar non-return to zero signaling. So I have already explained you polar non-return to zero signaling, which is also required for the case of your VPSK system. So again, here we need to have the polar non-return to zero signaling. Fine. So this has to be converted into polar non-return to zero signaling, and then this has to be demultiplexed into, because first of all we have to take the combination of the 2 bits. Okay, so this 2 bits has to be demultiplexed. Okay, demultiplexed. So we have to take the first bit over here and then the second bit at this point. Okay, so 1 bit is going to be to this particular channel. Okay, here it is just shown in this way. Okay, so sometimes it is also makes a confusion. So suppose that if we have a 0 1, for example, the bit which is coming as equals to 0 1, a corresponding polar non-return to zero signal line code will be generated. Okay, corresponding to 0 and corresponding to 1. So as we know that for the 0 there should be a negative impulse, and for the 1 there should be a positive impulse. So let us say when we have the negative impulse, okay, this negative impulse is going to towards this particular product modulator. This A1T represents our first pulse, okay, and this A2 represents our second pulse. So when it is 0, 1, this negative pulse is going to be multiplied here, and corresponding to 1, the positive pulse is going to be multiplied with this particular basis function phi 2. So here you can either also represent like two box, okay? And this first line is actually connected to the first box, and this is connected to the second box, okay? So here the meaning of the demultiplexing is that one, okay? Because we have generated the polar non-return to 0 signal. So first signal has to be multiplied here, and the second signal has to be multiplied here. So here you can see that if we have multiplied any signal, that should be means multiplied with the corresponding basis function. So we have the basis function phi 1t, which is equals to root over 2 upon t cos 2 pi fct, and here we have the another basis function phi 2t equals to root over 2t sin 2 pi fct. Okay, here from its nature itself, we can see that this two basis functions are actually quadrature phase, because it is having a 90-degree phase shift. Okay, we can see that it is a quadrature phase, quadrature carriers, you can say that we have the quadrature carrier. So that's why its name is also quadrature phase shift king. Okay, so here we have to multiply it with the first impulse, okay, and then positive negative impulse if it is 0, 1, and then it should be multiplied with the positive impulse, positive pulse, okay. And then this has to be added at this particular summer point. Okay, it has to be added at this point. And as I said that here it is going to be giving you corresponding to 0, it is going to be giving you 180-degree phase shift, okay, to this particular signal. And here it is going to give you no phase shift to the signal. And then the corresponding waveforms that will be generated has to be added. And then finally, this signal that we are going to get is a Qpsk signal. So you try to just correlate this diagram with this particular waveform. Okay, here we have generated Si1t, phi1t, and then here we have generated Si2t with phi2t. Okay, so this is whatever we have shown here. Okay, the same thing actually we have implemented in the diagram form. Okay, first we are taking the first bit, and corresponding polar non-return to 0 signal will be applied to this, and then this has to be multiplied with the basis function. Then correspondingly to this values of A1t, we are going to get these values, and again here we are going to get these values, and then this has to be summed up to get this particular Qpsk waveform, this waveform. Okay. So again, you can see that here we have taken the odd numbered sequence, and here we have taken the even numbered sequence. So the same thing here, you can say that if it is connected to this point, it is an odd number sequence. And when it is connected to the second box, it is a even number sequence. Okay? That way we can have this signals, and then it is generating the Qpsk signal. So receiving part, again, it is very straightforward. As I said that in the case of signal space representation, I told you that this received signal has to be multiplied with the same basis function. Okay, and then it has to be integrated over the bit duration TB. Okay, it has to be integrated. Fine. So if you integrate it, this is going to be give you. This is actually representing again your correlator. I told you with the previous thing that it is a correlator. Okay, so that will be a correlator. So this correlator will again give you a certain output. Okay, this is called as the in phase channel, and here it is a quadrature phase, quadrature channel. Okay, in phase channel, why it is in phase? It is cos 2 pi fct. It is our means in phase carrier, and this is our quadrature phase carrier. Okay, so therefore I am calling it as an in phase channel. So here again phi 1t has to be multiplied. It should be integrated. The signal that we are going to get is a certain value of x1. So there should be a decision device. Okay, if this value is greater than the threshold value, okay, then if it is greater than the threshold, it will be regarded as 1. If it is less than 0, then it will be regarded as 0. Okay. Similarly, again here the received signal is to be multiplied with the phi 2t. Okay, so again it will be integrated. So this is again a correlator part. Again we have to have a decision device. Okay, and then again there will be a decision making device that will be deciding if it is greater than the threshold, it will be 1. If it is less than threshold value 0, then it will be your 0. And then this will be multiplexed together, and then this bit sequence again can be recovered easily. So I hope you must be able to understand this. Okay, you must be able to understand this. So if you have any further doubt, okay, I hope this is already a very lengthy lecture, so I should stop here. Okay, I will be discussing the frequency phase shift keying. Okay, in the my coming lectures. Okay, because it is already a very lengthy lecture, I should stop here. I just wanted to make one point here that about the frequency shifting. In the last, even in the introduction of this, I explained you that in the case of FSK signal, what we have is based on the this particular bit sequence. Okay, whenever we are having a positive bit, okay, whenever we have this bit equals to 1, there will be one particular frequency is sent. Okay, and then we have the 0, then next another frequency will be sent. Okay, so basically 2 different frequencies are actually sent in the case of frequency shift keying. So generally this corresponding to 1, whatever the frequencies that we sent is actually called as the mark frequency. Okay, and a frequency that we sent corresponding to 0 is generally called as the space frequency. Okay, I will discuss this topic, okay, in more detail in the coming lectures, because it is already too lengthy. So let me stop here. Okay, if you have any further query, let me know with your comments. Okay, so thank you for watching this video. For the next lecture, please stay connected with the channel. So thank